So we've talked about what science is, the history of science, steps to do science, but now we need to actually look at the specific skills that scientists use. And a lot of these skills are math-based. So imagine you're flying an airplane, a jumbo jet, about, 8 miles high in the atmosphere, and you notice you're running out of fuel and you're only halfway to your destination. You know you're not going to have enough fuel to make it. Why did this happen? What are the consequences of this? And so this actually happened in 1983 on an Air Canada 747 jet. The amount of fuel needed for the flight was miscalculated because standard English units were used instead of the newly adopted metric system. So amazingly, the pilot was able to glide the jet safely to the ground and no one was seriously injured. So this shows that there's an importance to have a standard system of measurement units. So in the scientific community, we use the SI system of units, and it's the International System of Units. And this allows scientists to communicate effectively with one another. And so we're going to learn more about this system of units in these notes and a bunch of other ways that scientists communicate with one another. So the SI units is a measurement system used by most scientists, and it's based on the number 10. We like the number 10. It multiplies easily, it divides easily, and you can simply just move decimal points to transfer or to convert between different units. The units are multiplied or divided by powers of 10 to arrive at bigger or smaller units. This is just a fancy way of saying move the decimal. You either move it to the left or the right, depending on if you're multiplying or dividing. And then we use these things called prefixes to, we add them to the name of the base units to indicate the power of 10. So here, if we look at the table, we have a list of our base units. We have meter is the base unit for length. And if you look at the related SI units column, see meter, 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 all the way down. But the prefixes indicate a certain number. So kilo indicates 1,000. Deci means 0.1. Centi means 0.01, and so on down the line. So, we talked about that. So let's practice converting 3 meters into inches. So you should have a little cheat sheet that tells you some of these conversion factors. And so when we do this, you always start with what you're given. It's 3 meters. And you draw what we call railroad tracks. And on this bottom corner, you put the meters. So this is a math skill. When something on the top is the same as something on the bottom, they can cancel out as long as they're being multiplied or divided. And this horizontal line here is indicating a division that is happening. So you can look up on your half sheet of conversions, a conversion between meters to inches. And I believe it tells you that there's 1 meter in 39.37 inches. And when you are to the unit that you desire, inches, you can multiply across. So we'll take 3 times 39.37. Remember I told you that this horizontal line meant divided by everything that's on the bottom. In this case, it's just a 1. So multiply across, and you get 118.11 over 1, do the division, and you get 118.11 inches as your final answer. So what about another one here? Rod needs to buy 1 meter of wire for a science experiment. The wire is sold by the yard, not the meter. If he buys 1 yard of wire, will he have enough? So again, start with what you are given. He buys 1 yard. So 1 yard. And we need the unit of yard to go away, so we put it on the bottom. So when you look at your sheet, you might see that there isn't a conversion from yards to meters, which is our desired unit up here. But what you will see is you can go from a yard to inches, and I think the sheet tells you that in 1 yard, there's 36 inches. And notice how we're currently not in our desired unit of meters. So we need to add another section to this train track. And so now inches is going to go on the bottom because we want it to cancel out. And so from up top or your half sheet, you will know that there's 39.37 inches in 1 meter. Now we're to our final unit. So we can multiply across 1 times 36 times the 1 all over 1 times 39.37. And so one of these ones on top can cancel out with the 1 on the bottom. And we know that 36 times 1 is just 36. So we can take 36 divided by 39.37, and we will come up with 0.914 meters. So if he buys 1 yard, will he have enough when he needs 1 meter? And so the answer here is no, he won't have enough. So another area where we need to have the same units is when we look at temperature. The Kelvin scale is the SI unit for measuring temperature. The freezing point of water on the Kelvin scale is at 273 Kelvin, and water will boil at 373 Kelvin. And so some scientists will still use the Celsius scale, and then the good old United States still uses Fahrenheit. This table over here shows you how the different freezing points and boiling points of water vary between the 3 different temperature scales. So each 1 degree change on the Kelvin scale is equal to a 1 degree change on the Celsius scale. So when you're converting from Celsius into Kelvin, you add 273. And when you go from Kelvin to Celsius, you would subtract it. And then when you have to throw in the Fahrenheit mess, you need to use these 2 formulas, one of these 2 formulas. So going from Celsius to Fahrenheit, you take your Celsius, your given Celsius temperature, multiply it by 1.8, and add 32 to get your Fahrenheit temperature. And the reverse is true from going Fahrenheit to Celsius. You take your Fahrenheit temperature, subtract 32, and then divide by 1.8 to get your degrees Celsius. When you are using these, your order of operations from math class have to be followed. So let's go ahead and practice this. So the problem says to convert 10 degrees Celsius to Fahrenheit. So we are going to be looking at using this formula because we're going from Celsius to Fahrenheit. So we take our given Celsius temperature, which is 10 degrees Celsius, multiply it by 1.8, and then add 32. So when you do that, you should get 50 degrees Fahrenheit. Another practice, the weather forecaster predicts a high temperature of 86 degrees Fahrenheit today. What will the temperature be in Celsius? So now we're going from Fahrenheit to Celsius, so we need to use the formula over here. So you start with your given Fahrenheit temperature, which in this case is 86 degrees Fahrenheit. You need to subtract 32 from the 86 and then divide by 1.8. So when you do that, you get 30 degrees Celsius. So when we get into the actual lab, you're going to be asked to use graduated cylinders rather frequently. So a graduated cylinder is used to measure the volume of a liquid. So to use one, you need to place the cylinder on a level surface before adding any liquid. And then you move your eyes so that they're at the same level as the top of the liquid line. So you need to read it at eye level. And then read the mark on the cylinder that is at the lowest point of the curved surface. And we call that curved surface, it has a name, it's called the meniscus. So if we look at the examples over to the right, your meniscus is right here. It's a little curve. And so you read it at the bottom of the meniscus. So this one is 3, 1, 2, 3, 4, 5. So these lines are marking by 2, so 3.2, so 3.4 milliliters or whatever unit they're using. The one to the right here is curved right here. The lowest point of that curve is sitting right at 5, we'll call it milliliters. Rulers and meter sticks. It is so important that you use the metric side of your ruler or meter stick and not the English side. The English side is the side that's going to look most familiar to you because it's going to be in inches. Okay. When you look at these rulers, you're going to see that there's the label of mm, and that's indicating millimeters. That is telling you the smallest markings. So up here, each one of these little dashes is 1 millimeter. The bigger numbers here are actually representing centimeters. So let's practice looking at line A over here. We're on the metric side because it's showing us millimeters. And I want to know how long from the end of the ruler to line A is. And let's say in centimeters. So A in centimeters equals, so we're at 1 centimeter here. And we go to this line. And each line counts as 1, so 1, 2, 3, 4, 5, 6, 7. So this would be 1.7 centimeters. And now if I ask for line A in millimeters, you could simply count every one of these tick marks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and get 17 millimeters. However, you might know that in 1 centimeter, there are 10 millimeters. So here, since you get to the 1, you can just know that there are 10 millimeters there. Let's practice with line C. How about line C in millimeters? So line C is right here. Goes past the 2, so we know that's 20 centimeters. So then there's 20 millimeters, sorry. So we can count 1, 2, 3, 4, 5, 6, 7. So we know it's 27 millimeters. One confusing part of science is the terms accuracy and precision. And when we talk in everyday conversations, we throw around accuracy and precision interchangeably. They get to be used to mean the same thing. However, in science, that is not the case. So when we talk about accuracy in science, we talk about the closeness of a measurement to the accepted value. Precision, on the other hand, refers to the exactness of a measurement. So it kind of helps to think of this as like shooting at a target where you aim for the bullseye. The bullseye would be an example of your accepted value, the bullseye. So in this particular target, there were 3 shots taken. And if they were 100% accurate, all 3 of those shots would have landed in the bullseye. So it's not 100% accurate, but it's not like the shots missed the target. So it's not very accurate. However, it is very precise because these 3 shots are almost in exactly the same spot. They're exactly grouped together. I think of precision as a close group or grouping. So if we look at this target down here, you'll notice that all 5 shots, they're pretty well spread out. So they don't have a close group. So this is not precise. And then if we look at the bullseye, as a group, they're not very accurate because they're not hitting the desired target. If we look at target number 3 here, are all 4 shots on the bullseye? And they are. So that makes this target very accurate. And we have exactness because all 4 shots are very close to one another, making it precise. So when we do scientific experiments, you have to keep records of your data and your observations. So here are some rule of thumb or guidelines to follow. So for one, write in permanent ink for your records. And so for us, it's really not a big deal because you'll be doing most of your record keeping on your iPads. You need to record all of the steps of the procedures. You need to make sure you record all measurements and observations. You can use drawings or sketches as necessary. And then make sure you write the dates on your entries and on your drawings so you have a clear timeline. All right, now we start to get into some more math. Derived quantities or numbers are numbers that are calculated from 2 or more different measurements. So examples here that you're probably familiar with are area and volume, and maybe new to you would be density. All 3 of these require math in order to get the answer. So over here, area would be length times width, and the volume, length times width times height. We have to do the math, or the multiplying here, in order to get the answer for volume and area. So in order for us to use those formulas, all of the measurements must have the same units. So that means your height could be in meters, your length could be in meters, but your width couldn't be in inches because they all have to be the same. And then lastly, when you come to your answer, you've done the math, you get a number, your number must have a unit with it. In my class, you will lose half a point if you give me a number with no unit. So if the answer is 3.2 meters, and you only give me 3.2, you will automatically lose half a point. Significant figures is a fancy way of reporting answers. This uses the correct number of digits in an answer that is based on the least precise measurement used in a calculation. So when we look at a bunch of numbers, and when we think about ethics and being biased, we want to use the least likely number to be correct. It gives us some room of, okay, so my measurements weren't very good, they weren't very precise, and so if I'm reporting the worst case scenario, I will know how far off I am. And so when we look at a number, so let's say 23.05, this particular number has 4 significant figures. All 4 of these digits are considered significant. Whereas, let's say a number like 0.003145, you cannot count these zeros as significant. They are not. They're considered placeholders. Instead, only the non-zero digits are significant. So this one would also have 4 significant figures. So when we do any kind of math, multiplying, dividing, adding, and subtracting, there are certain rules with significant figures you have to follow. So when you multiply or divide, your final answer has to have the same number of significant figures as the measurement having the least number of significant figures. So in this case, we're multiplying 123 by 5.35. Each of those digits, the 1, the 2, and the 3, are significant. So there are 3 sig figs. And 5.35, all 3 of those are also significant. So your answer can only have 3 significant figures in it. So when you multiply this out onto the calculator, you are going to get 658.05. This number has 5 significant figures. And your final answer cannot have 5 sig figs. So you start from the right and you start to chop them off until you only have 3 left. So your final answer would be 658. If this 0 right here had been a 5 or bigger, we would have rounded our final answer to 659. So rounding rules you apply those rounding rules. So when you add or subtract, your final answer has to have the same number of digits to the right of the decimal as the measurement with the fewest number of digits to the right of the decimal. So we have 97.3, and there's 1 digit to the right of the decimal. And 5.85, here we have 2 digits to the right of the decimal. So when you add this up, you'll get 103.15. So our final answer can only have the 1 digit past the decimal. So we're for sure on the 103 point. And so since this number is a 5, this 1 would get rounded up to a 2. Scientific notation is something I think you will touch on in your math class too, but we use it a lot in science. This is a way of writing very small or very large numbers, and you use exponents in the format of a times 10 to the b, where a is a decimal number between 1 and 9.9999999, and b is an exponent, almost always a whole number. So for example, in scientific notation, 300 becomes 3 times 10 to the second. So let's work on how to do this. So when you have a really big number, your decimal is always at the farthest right. And so we're going to move this decimal somewhere in this line of numbers so that we get a number between 1 and 9.999. So the only place where you can put this decimal to get a number that fits that rule is between the 4 and the 6. And then you write the times 10, and now you have to figure out the exponent. So if we've moved the decimal to here, in order to get it back to its starting spot, we're going to move it 1, 2, 3, 4, 5, 6, 7 places. That is the value of your exponent, would be the 7. So another practice, here we have 6,720. Our decimal's at the far right. And so where do we put that decimal to follow the between the 1 and 9.99 rule? So the answer here is going to be 6.72 times 10. So if we place our decimal back up here, and we want to move it back to where it was originally, we're going to move it 1, 2, 3 spots to the right. All right, so last example. Here we're given a decimal, and so it's placed over to the left. So we need to move it again so it falls between 1 and 9.99. So here we have 4.8. And then keep it the same, times 10. So we've moved the decimal here. And now this time, to get it back to the original place, we go 1, 2. But this time, since we moved it back, we had to go to the left. You have to put a negative out front. So scientists use tables and graphs to organize their data. A table looks like a spreadsheet, and it's got columns and rows. Sometimes it's hard to see patterns or trends in data tables, but they are useful to keep data organized. Graphs help give a visualization to the data. We have bar graphs, circle graphs, and line graphs. Bar graphs compare values for different types of things. Circle graphs show the percentage of the whole. Remember, the whole thing would be 100%. And then line graphs show changes over time. Descriptive statistics, again, a lot of math here, but I think these are all words you should have heard before. The mean is the average value of a set of measurements. You calculate it by adding up all the numbers of individual measurements and then dividing that number by the total number of measurements. So, for example, if we were to calculate the average in this data table over here, we'd take 150 plus 50 plus 80 plus 50 plus 70, and we would get 400. And then since there are 1, 2, 3, 4, 5 measurements, we would divide 400 by 5 and get an average of 80. The range is the total spread of values in a set of measurements. It's calculated from subtracting the smallest value from the largest value. So again, using the same data set, our largest value is 150 minus our smallest value, which is 50, and our range would then be, 100. Scientists also use models to represent their information. This could be a representation of objects, systems, or processes. They provide a way to investigate things that are too small or too large. Or too complex, or too far away. So example would be like a road map or a globe. allow us to see things on Earth's surface that we wouldn't be able to see because Earth is too big. Lastly, we need to be safe in science. You will see an assortment of safety symbols as you go through, and you can take a look at those. And then some basic safety rules. You need to wear goggles when you're told to, closed-toed shoes, have your long hair tied up, don't eat or drink in the lab, don't work alone, no unauthorized experiments, never point the open end of a test tube at anyone, make sure you wash the glassware and counters when you finish, make sure you wash your hands, always add acid to water, and then add the acid slowly. Immediately tell your teacher if something goes wrong. You will be in more trouble if you don't tell me and you try to hide it than if you just come to me and say you made a mistake.